Hello, this is Andy from the Engineers Academy, and in this video we're going to be discussing heat engines, heat pumps and reverse heat pumps. We're going to be looking at some of the similarities and differences between these types of systems, as well as considering some of their applications. So first of all, let's begin with heat engines. Now, heat engines are systems that are specifically designed to convert heat energy to mechanical work. One such example are steam turbines and steam turbine plant. Now, steam turbine power plant is typically modelled using something called the Rankine cycle. So if we begin on the left-hand side, we have a number of different components. We have a pump, we have a boiler, we have a turbine, and we have a condenser. I've numbered various different locations on the schematic, so position 1 is before the entry to the pump. Now, the purpose of the pump is to pump the water into the boiler. As the boiler receives that water, it's going to heat it and convert it into steam. Once we have steam, we're then going to enter the turbine, and the purpose of the turbine is to expand that steam whilst creating mechanical work. The process of expanding the steam is going to cause our turbine to spin. Immediately after the turbine, we have the condenser. And the purpose of the condenser is to convert any remaining steam back to water before it returns to the pump. So moving over to the right hand side, we can begin to consider the pressure and volume changes within this system at different points in the process. Now, if you've watched our earlier tutorials, then you'll already be familiar with this type of diagram. But essentially what we have on the left hand side of this curve is we have water on the left hand side. Underneath the curve, we have a mixture of water and steam. Essentially what we have under here is wet steam, where we have a combination of water and steam as it's converting from water into pure or superheated steam. If at any point we're sitting directly on this curve here, we would have dry saturated steam, so we're at the point where all of the moisture has been removed. And over on the left hand side here, we have what we call wet saturated steam. So we're on that point where we're converting from water into steam. So as we mentioned then, moving from position 1 to position 2, we're pumping the water, or we're increasing the pressure of the water. So that would be represented on our pressure volume diagram like so. The volume is unchanged, but the pressure is increasing. Now, our boiler and our condenser are both considered to be constant pressure processes. So we're heating the fluid at constant pressure. Well, when we heat a fluid at constant pressure, it expands. So although our pressure remains constant, moving from 2 to 3, we do see an increase in volume. The expansion of our steam is known as an isentropic process, and we'll talk about that a little bit more in a moment. But when we expand the steam through the turbine, the volume increases and the pressure decreases. And we see that represented on our PV diagram like so. And finally, in the condenser, we're removing heat. Removing heat at constant pressure means the volume is going to decrease. So moving from 4 to 1 is represented like so on our PV diagram. Now, we've made various assumptions here that wouldn't necessarily be the case, but this is really just for illustration purposes. We've assumed that in our boiler, we have water entering and we have superheated steam leaving the boiler. Recall that anything to the right of the curve is superheated. We've then expanded our steam, and we've assumed that after the expansion we have a mixture of steam and water because we're inside the curve here. After the turbine, we cool the fluid further, so our mixture of water and steam returns to wet saturated vapour here. So next, let's consider our temperature entropy diagram for this cycle. Now, before we do this, it's important to remind ourselves what we mean by entropy, and I've got a bit of a definition here for entropy. Entropy is the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. Work is obtained from ordered molecular motion, so the amount of entropy is a measure of the molecular disorder or randomness of a system. Now, if we pick up on a couple of points here, the first thing that it tells us about entropy is that energy is unavailable for doing useful work. It's basically energy that we can't draw out of that process in order to produce mechanical work within our turbine. The energy that we can withdraw is called enthalpy, and the energy that we're unable to withdraw is entropy. So the entropy, if you like, remains in the system. We mentioned that within our turbine that was an isentropic process or a constant entropy process. So what we're basically saying there is we're removing the useful work, but the non-useful work remains behind. So the expansion of our steam through our turbine is essentially an ideal process because the only energy that remains in the system or in the working fluid is the entropy or the non-useful energy. So let's return to our schematic diagram then and recall that position 1 to 2 was pumping of the fluid. Well, our pumping of the fluid and our expansion of the fluid are both isentropic processes. So when we pump the fluid and we increase its pressure, we also increase its temperature. Recall that when we increase the pressure of a fluid, we force the particles closer together, the particles vibrate and they generate heat, therefore an increase in temperature. We then move into our boiler from 2 to 3, and there's a couple of things to note here. The first thing that we need to do is increase the temperature of the water. Now the temperature of the water is going to continue increasing until it reaches its boiling point. Once it begins to boil, we continue putting energy into the system, but the temperature no longer increases. Now a perfect illustration of this is if we're boiling water at atmospheric pressure, then we increase the temperature of the water to 100 degrees C. The water remains at 100 degrees C and begins to boil, and it will remain at 100 degrees C until all of that water is evaporated and becomes steam. If we were able to capture that steam and continue heating it, its temperature would begin increasing again, and then we get what's called superheated steam. So in the boiler, the water reaches its boiling point, it boils until it's all evaporated, and then once it's all evaporated, we continue heating it to create superheated steam. Next, we expand our steam, and once again recall that here we're going to have a mixture of water and steam, or a wet vapour if you like. And next, we're going to convert that remaining steam back to water. So over here we have the wet saturated vapour. Now the same as when the water's boiling, its temperature remains constant. Well, the same is true when it's returning from steam back to water. The temperature remains constant, but its entropy decreases. So we see that represented like so on our temperature entropy diagram. So next, let's consider what we mean by a heat pump as opposed to a heat engine. So the difference between a heat pump and a heat engine is that a heat engine converts heat to mechanical work, whereas a heat pump transfers energy into a system. Now we're going to discuss the contradiction with the second law of thermodynamics, because what we actually see happening here is we actually move heat energy from a colder environment into a warmer environment. And that's against the natural flow of energy, as we'll see shortly. We have various different examples of heat pumps. We have ground source heat pumps and we have air source heat pumps. And this particular type of system operates on something called the vapor compression cycle. So as I mentioned there, we have a contradiction with the second law of thermodynamics. Now the second law of thermodynamics states that heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. So what we're basically saying there is if we have a hot fluid and a cold fluid, the natural flow of energy is always from the hot fluid to the cold fluid and not in the opposite direction. What we're going to see here with heat pumps is we can actually manipulate a refrigerant in order to achieve flow of energy in the opposite direction. So now on the left-hand side, we have a schematic for a heat pump. Once again, we have various different components. We have a compressor, which is used to compress the working fluid. The working fluid in this instance is a refrigerant. We have a condenser. Now, the purpose of a condenser, as we said previously, is to remove heat energy from the working fluid. We have an expansion valve, and the expansion valve is used to expand the working fluid, and in doing so, its temperature is going to drop. Next, we have an evaporator that's used to heat the working fluid. So I've made some annotations on this schematic. I've indicated that the condenser is located in a room and the evaporator is located outside. With this being a heat pump, or an air source heat pump in this case, what we're basically doing is we're using hot refrigerant to heat the air in the room. But the reason we have our contradiction here is because, let's say for argument's sake, we want the temperature in our room to be 20 degrees. Now the outside air temperature might only be 10 degrees. So what we're actually doing is we're removing heat energy from the air outside and we're pumping that heat energy back into the room, despite the fact that the room is already at a higher temperature than the outside air. And we'll talk about how we can do this as we go through this section. So one difference we observe here is that we have a compressor instead of a pump. And the reason we have a compressor is because when the refrigerant passes through that component, it's already a gas. Moving from 1 to 2 then, we have a dry saturated fluid entering the compressor, and exiting the compressor, we have a superheated fluid at a higher pressure. When we compress the gas, its volume decreases and its pressure increases. As we'll see in a moment, this is also an isentropic process. So we have an ideal compression in order to increase the pressure and reduce the volume of our gas. The other thing we'll notice in a moment is that during this compression, the gas or the refrigerant is going to heat up considerably. So entering the heat exchanger in the room, we have high pressure, hot refrigerant, and that refrigerant is going to give up heat energy to the room. Inside that heat exchanger, we're going to have air being blown over the hot coils, and those coils are hot because they contain the hot refrigerant. As the refrigerant passes through that heat exchanger, the air is going to heat up, but the refrigerant itself is going to cool down. And here we see it cooling down from superheated vapour to wet saturated vapour here at position 3. Now the wet saturated vapour is then going to enter our expansion valve, and passing through the expansion valve 3 to 4, the fluid's going to expand, meaning its pressure is going to decrease and its volume is going to increase. This process here isn't isentropic, instead it's a constant enthalpy process. So we see pressure decreasing and we see volume increasing. The significance of this being a constant enthalpy throttling process will become clear when we start to carry out calculations involving heat pumps and reverse heat pumps. So finally, we have the cold fluid. It's cold because we've removed energy from it, and then we've also expanded it. So this is the coldest point for our refrigerant. But that cold refrigerant is then going to be passed through a second heat exchanger which is located outside. The temperature of the refrigerant is going to be lower than the outside air, so it's actually going to gain energy as it passes through the heat exchanger, returning it back to our dry saturated vapour point over here on the right hand side at position 1. The cycle then continues back through the compressor, back through the condenser, and so on. So next let's consider the changes in temperature and entropy as we go through this cycle. Positions 1 to 2 we said was isentropic. As the gas is being compressed, its temperature is going to increase. It's constant entropy, so we see that line moving directly upwards, an increase in temperature at constant entropy. We then pass through our condenser. So this is where the hot refrigerant is giving up heat energy to the room. So as the refrigerant gives up heat energy to the room, it's going to cool down. The superheated vapour cools down until it reaches its dry saturation point. Energy continues to be removed, but this is now at constant temperature because we have a change of state from fluid to liquid. And in this example, we're cooling the refrigerant until it reaches the wet saturation point here. 3 to 4 is our expansion. We have a decrease in temperature and we have a slight increase in entropy. This is due to the viscous effects of the fluid as it passes through the valve. 4 to 1 we have the evaporator, where we're heating our wet vapour, and we're heating that wet vapour until it becomes dry vapour at the same temperature. The temperature remains constant because we're still changing state as we move from 4 to 1. Now once again, just to reiterate the contradiction with the second law of thermodynamics, we've given the example where the outside air might be at 10 degrees and the room is being maintained at 20 degrees, so the energy is flowing from outside to inside against the natural thermal gradient. We would expect the hot room to give up energy to the outside air, but because we're manipulating the refrigerant in this cycle, we're actually able to encourage heat energy to transfer from the colder region to the hotter region. So next let's look at reverse heat pumps, and we're going to see a similar contradiction here, except once again we're going to have energy transferring from a cold space to a hot space. The difference here is that our cold space is going to be our room and our hot space is going to be the outside air. So this is typical of what we would see in a refrigerator, or for the purposes of our discussion here, in an air conditioning system. So the first thing you'll know is that all of our components are exactly the same. We have a compressor, we have the outside heat exchanger, we have an expansion valve, and we have the inside heat exchanger. The only difference here is that the refrigerant is moving in the opposite direction. So this time we compress our refrigerant before it moves to the outside heat exchanger, or the condenser. So once again, we're compressing that dry saturated vapour, and in doing so, its pressure increases, its volume decreases, and therefore its temperature is going to increase. What we end up with is superheated refrigerant or superheated vapour. This time the refrigerant is hotter than the outside air, so as it passes through the outside heat exchanger, it's going to give up heat energy to the outside air. As it loses heat energy, it's going to cool down. Now once again, because this is a constant pressure process, the cooling down of that refrigerant is going to cause it to contract, and as it contracts, its volume decreases. 3 to 4 then is our expansion valve. So when we expand the vapour, its pressure decreases and its volume increases. Once again, this is a throttling process or a constant enthalpy process. And it's at this point that our very cold refrigerant enters the heat exchanger inside the room. So what we have is cold refrigerant in the heat exchanger, and the warm air in the room is being blown across that heat exchanger, which contains the very cold refrigerant. So what we're going to see this time is heat energy being removed from the room or drawn out of the room and moved into the working fluid or the refrigerant. Therefore, the temperature of the refrigerant increases, but the temperature of air in the room is going to decrease, which is our desired effect. The refrigerant is heated at constant pressure, so we see pressure remaining constant but volume increasing. So now let's relate this to the temperature entropy diagram. 1 to 2 is compression. We've already mentioned that it's isentropic compression, so entropy remains constant, temperature increases, and we're going from dry saturated vapour to superheated vapour. So now our very hot refrigerant is going to move to the outside heat exchanger. The refrigerant is hotter than the outside air, so it's going to give up energy to the outside air. Now bearing in mind the outside air could still be hot, it could be 30 degrees Celsius as an example, but because the refrigerant is hotter, it's going to give up energy to the outside air. In doing so, the superheated vapour cools and it then changes state until it reaches the wet saturated vapour point. 3 to 4 is expansion, so when we expand that vapour it's going to cool down further. So what we end up with once again is our very cold vapour. This is the coldest point for the refrigerant in the cycle. So our very cold refrigerant this time enters the room heat exchanger. As the air in the room passes over the heat exchanger, the refrigerant's going to heat up, but the air in the room is going to cool down. So we have that cooling effect associated with air conditioners. So just to summarise, in this video we've discussed heat engines and how a heat engine is used to convert heat into mechanical work. We've also discussed heat pumps, which are used to transfer heat energy into a space, and we've compared those to reverse heat pumps, which are used to transfer heat energy out of a space. In the case of heat pumps, we're transferring heat energy from a colder region or outside air into a warmer region or a room in the case of an air source heat pump, and we discussed why that contradicted the second law of thermodynamics. We then looked at reverse heat pumps, and reverse heat pumps also have that contradiction because what a reverse heat pump does is it removes heat energy from a colder region and transfers that heat energy to a warmer region. We use the example of air conditioners, where colder air in a room is actually transferring heat energy to the warmer region of the outside air. Now, although we have that contradiction in the case of heat pumps and reverse heat pumps, the way we achieve that is by manipulating the working fluid, which is typically a refrigerant.